Today's lecture covers GPS data format. This will highlight the core type of data that's transmitted between a GPS receiver and some device like a precision ag display so that it can be utilized by that display for our applications. So the question exists: I have a GPS receiver out on my tractor somewhere, I have some sort of display or interface in my tractor, and how do I get data from one to the other? There are a variety of different ways to do this to get data transmitted from the receiver into the display. And of course they have to have a similar type of format in order for this to work. The varieties include RS-232, which is a type of serial communication, CAN bus, which is a newer type of communication protocol used on many pieces of ag equipment, or it can still be wireless through a Bluetooth connection, particularly if you're using PDA based handheld collection units. Now, the type of format has to match at both the transmitter and the receiver. So what I'm showing on the screen, a John Deere Starfire ITC receiver talking to an Ag Leader Insight display, does not typically happen if you use the basic communication protocol of each. The Starfire prefers to communicate over CAN bus, whereas the Insight from Ag Leader would prefer to have an RS-232 GPS input. The Starfire receiver can be configured for RS-232 to make this connection work, and is a requirement if we're trying to achieve communication with products that aren't based on the same generic protocol. So the data that's transmitted from most receivers comes out serially. And what we mean by serially is we mean the data is transmitted over a single wire from the GPS receiver into the GPS display or the precision ag display. And so on that single wire you will see bits of information over time, or voltages that go high and low. And the pattern in which these voltages go high and low is somewhat of an electronic Morse code that can be deciphered into real information in the display. And the most common or the most generic protocol for this is RS-232, which is often called serial communication. Here's an example of an RS-232 cable. RS-232 cables are highly identifiable by the type of connector they have. This is a standard RS-232 connector. It's called a D-sub connector, or D-sub 9. The reason it's called a D-sub, the D stands for or indicates the pattern. It's noticed here that this has a D-type shape to it. The dash 9 indicates that it's a 9-pin connector. The sub indicates it's a sub-miniature type connector. But in practice this would be a DB9 or a D-sub 9 GPS connector. Now, the type of connector it has, whether it be male pins or female pins, depends somewhat on the application. Shown on this diagram are two different configurations of the same GPS receiver running to either a set of female contacts on the left or male contacts on the right, and it depends what the final destination of this information is. If it's going to a computer, then we would use the configuration on the left. If it's going to a PDA or other type of handheld or display device, then we use the application on the right. When it comes time to decide your exact configuration for your piece of equipment, this is where the manufacturer would often provide the cable that would ensure that you'll have the right connection. So a little more detail about this cabling. On one side of the device will be a computer or a GPS display. On the other side we have the GPS receiver itself. There are 3 pins that connect these two devices. There's a ground, a transmit, and a receive. But notice that on one side, the GPS transmit, pin 2, has to connect to the computer receive, pin 2. So the pinouts are actually reversed in these two applications. If we don't correctly wire it, and we try to connect the transmit of one to the transmit of the other, we get data that's trying to pass on the same line, and we have no information that's able to, or no data that's able to get into our precision ag display. This is often a common problem or a common troubleshooting step that has to be dealt with when trying to get GPS data to pass through. If this is the case, if we're wiring harnesses provide this type of problem, the solution to this is to utilize a null modem. Null modems are cables that intentionally flip wires 2 and 3 from one side of the connector to the other. And these are commercially available either as wires or as small little plug-in devices which enable the null modem functionality. Just like we've had to set up many different types of communication protocols for RTK, the same thing exists for RS-232 communications. In this case, we've got a variety of different indicators. Baud rate indicates the rate at which the message are transmitted. This means the speed at which each bit or piece of information is sent. Typical baud rates that we use in agriculture are 4800, 9600, and 19200. The message format is the type of data that's transmitted with each individual character of GPS data. Things to consider here is that the GPS application always uses 8 data bits. So when setting up the GPS unit, or the receive unit, we typically would use 8 data bits, no parity, and 1 stop bit. This information, these setup pieces, will be specified by the GPS receiver and must be correctly set in the GPS display in order to enable communication. Here's another example of a really traditional GPS serial application. I've got a baud rate that's an option, I've got data bits that are options, I've got parity that's options, stop bits, and flow control. A typical GPS application would be shorthand notation of 4800 8N1, which stands for 4800 baud, 8 data bits, no parity, 1 stop bit. And so in the manual of a GPS receiver or device, you may very well see this notation where the 8N1 typically doesn't change for GPS receivers, but the 4800 will absolutely change depending on the speed at which the receiver is set to. And likewise, you're often able to change this baud rate through the Precision Ag display to set up your receiver to send at a different rate. So what's the data itself look like? Well, the GPS data is made up of several GPS strings. GPS strings indicate unique pieces of information that are provided by the GPS receiver. Each string is unique and can provide things like position information, latitude, longitude, elevation, date and time, speed, correction type, number of satellites in view, PDOT values, a variety of really key information understanding the quality of our GPS unit. There are a variety of different GPS data strings that are available from a GPS receiver. These are standardized under the indicator of NMEA. So these are typically called NMEA GPS data strings. Each of the data strings begins with an indicator that tells us what type of message it is. For example, a very common indicator is the GGA message, which includes core information like time, position, and GPS fix related data. There are other messages that are used, including things like messages that tell us how many satellites are being accessed, speed at which we're traveling, PDOP levels, and other quality indicators for GPS. This page shows an example breakout of a GGA-based message. The GGA message starts out with an indicator, GPGGA. The last 3 characters tell us what type of message it is. At that point, we have a set of data which is comma delimited. And by knowing what each one of the columns or each one of the data sets between the commas indicates, we're able to decipher this into usable information. The table below shows what each field consists of. Field 1, which is 15, 19, 24, is the UTC time, or the universal time, of the position fix in hours, minutes, seconds. So this will be 15 hours, 19 minutes, 24 seconds. The next piece of information, 3723.45444, is the latitude position of the fix. We'll look at each of these values in a little bit more detail now. Here's an example of a typical GGA NMEA string. First field tells us the time of day. Second field gives us the latitude. The next field tells us the direction of latitude, in this case north. Next field is longitude, followed by the direction of longitude. Then we have the GPS quality, number of satellites in use, the h-stop of those satellites, the antenna height, and the antenna height unit of measure, which in this case is meters. And this would be antenna height above mean sea level. Now the key thing that we still don't have, still isn't fully comprehensible, is the units for latitude and longitude. Certainly we wouldn't be 3235 degrees latitude. These are actually a set of mixed characters in order to somewhat compress the latitude data. In the next slide we'll take a closer look at how we convert these latitude and longitude values into usable numbers. So let's talk through converting these latitude and longitude coordinates. In the NMEA data, latitude and longitude are represented as degrees minutes format. We typically want our information in terms of decimal degrees for latitude and longitude. It's a simple conversion between the two, knowing that 1 degree is equal to 60 minutes of latitude or longitude. Here's an example of that type of conversion. The latitude we saw previously was 3235.987632. Well, the first two digits represent the degrees of our position, which is 32 degrees. The rest of the digits then indicate the minutes component. In this case, 35.987632. To obtain a decimal degree format, we simply take the degrees value and add that to the minutes divided by 60. In our case, we take our 32 plus our minutes divided by 60, we end up with 32.599793. This is the GPS position in decimal degrees. The number of digits we have will vary depending on the type of receiver and the resolution that it provides. The UTC time that's provided is actually the time at Greenwich Mean Time in England. It must be offset for a local time zone to get a local time. In this case, here in the central Midwest, we're a 6-hour UTC differential from what the UTC time actually is. The GPS quality indicator, which is part of many NMEA strings, indicates the type of GPS fix we have. 0 being no GPS fix, 1 being GPS fix with no differential correction, 2 being DGPS, 4 being RTK fix, and 5 being RTK float. The update rate on a receiver is also an important factor. This tells us how many times per second the GPS receiver provides new GPS information. This is typically represented in terms of hertz. Hertz is the frequency, or 1 over the time between messages. So a 1 Hz receiver transmits 1 message per second, whereas a 10 Hz receiver transmits 10 times per second. The update rate is important for some of our automation systems, and we'll talk about this throughout the course of the semester.